technology conference and technology doesn't work.
We're on.
So hello everybody. It's my great pleasure to introduce George Denezis. He's a researcher at the Catholic University of Leuven in Belgium, and his work focuses on anonymous communications, and his talk will be on traffic analysis. And welcome, George.
Thank you, Andreas. It's a great pleasure to actually be invited to speak at the CCC. A few years back, I did talk about some preliminary work I was doing as a young research student on the traffic analysis of HTTPS traffic. And then 2 years ago, I spoke about the mixed minion format, which was on anonymizing communications. So now I'd like to give you a slightly more high-level talk about this kind of new discipline that is emerging from some body of work that a lot of researchers have been working on in the last 5 years, which is the field of traffic analysis. I'm very excited about it, and I hope I can actually share some of this excitement with you. Now, this is a talk about traffic analysis. I'll talk about lots of cool, neat tricks without going too much into detail on any of them. I do actually know the details of most of them, so if you want, you can challenge me to go into them if you're particularly interested. I'd like to, of course, take a historic overview of traffic analysis and present first its military root. Like most of the security technologies we're using today and we're thinking in the open, traffic analysis has originated actually from the military, and the military has much more experience in it probably than we have, since we're only beginning. Then I would like to set traffic analysis issues on the internet and the public networks as we know them, and then discuss a bit about how to extract and use location data and extract from them high-level intelligence rather than just bits and bytes at the network level. Of course, no talk on security should avoid defenses, even though the field of defending against traffic analysis is quite young. And I'm going to then present a few policy issues at the end. Now, let's first define what we're going to be talking about. What we are interested in is a class of techniques that use traffic data in order to extract and in order information or in order to generally violate security policies of secure systems. Okay? Now, this is opposed to interception of content of communications or cryptanalysis, which is breaking basically the ciphers that encrypt the content of communications. And traffic analysis is a set of disciplines that use traffic data. Now, what are traffic data? They are the identities or call signs of communicating parties. Okay? Alice and Bob as names are traffic data. They are, of course, the time and duration and length of communications and transmissions. Then, of course, these days, with mobile devices everywhere, traffic data is often the location of the device, or in GSM networks, the towers you're talking to, or the towers you can see, and so forth. In Wi-Fi, it is the access point. And throughout this talk, please note that I'm not going to be talking about the use of content of communications, just this high-level information of who is talking with whom. Now, the controversial starting point for this talk is a quote that you can find in Susan Landau's and Whitfield Diffie's book, Privacy on the Line. They were discussing about what was known as the crypto wars, i.e. the attempt of the US government and other governments to restrict the use of cryptography in the 90s. And the quote in this book is quite challenging because they say that it is traffic analysis and not cryptanalysis that is the backbones of signal intelligence. Okay? And we are going to see to what extent that is true, but it kind of highlights the importance of traffic analysis over what we conventionally look at when we think of security. And the question, of course, is that was the case when it came to signals intelligence, i.e. competing armies trying to get intelligence about each other. But then, how is that true for the internet today, and how we're going to be seeing this field being applicable to civilian communication systems? So let's start from the military world. My main source here is Herman. He wrote a very interesting book called Intelligence Power in Peace and War. And Herman was the chair of the Joint Intelligence Committee in the UK that is running one of the biggest spy operations in the world. And he said that about traffic analysis, that it allows basically people to find the target's locations, the order of battle of the units, and the movement of units. This is its tactical information. So it's already important for an army to use traffic analysis and analyze patterns of traffic to find targets, order of battle, and movement. But he also said that looking just at who is talking with whom on a battlefield allows you to discern the intentions and the state of minds of the enemy. Okay? And this is already quite high-level information. It's not just about which units are where, but whether they are ready to actually engage in operations, or whether they're just assuming a defensive role, whether they expect to be at war soon, or whether they expect to actually disband soon. Okay? And he really created, and he has a very nice picture in his book, which I didn't actually copy, of a pyramid, where he says the bulk of the information is actually from RF direction finding, okay, in signal intelligence. So you listen and try to find where are the points that are transmitting. Then you use traffic analysis. You look at who are these people and what are their call signs, how often they are transmitting, at what frequencies and all that stuff. And then only when you have performed traffic analysis and you have selected some targets of interest, you actually throw your clever mathematicians to do cryptanalysis and try to break the codes. If you try to break all the codes, probably you will not have enough mathematicians' time, and definitely you will not have enough translators, transcribers, and intelligence personnel to even read the communication. So traffic analysis is used in this context as target selection. And the second way of thinking it is again presented by Whitfield Diffie, in the context of information warfare, and this is maybe a bit of an esoteric slide, but it kind of really goes to the point of what are traffic analysis and traffic analysis prevention techniques, which is, he says, Whitfield Diffie says, what is basically information warfare? His first comment is, it's not just a bomb in the computer room of your adversary. And he points out that modern warfare has dramatically changed, and he presents as the example air operations. In the Second World War, there was a very particular cycle in engaging in a bombing raid, for example. You were sending your reconnaissance planes, they were taking pictures, you were selecting the targets when they were coming back and the pictures were developed. Then the bombers went away, they bombed away at night, they came back. Then you send the second wave of reconnaissance planes, they took more pictures, they came back, they got developed. You looked how the targets were destroyed or not, and then you recurse. Okay? And that creates a cycle of operations. This cycle takes 3 days or so. Okay? Now, he compares that picture from the Second World War operations to the Iraqi war, the first one in '91, where he said that basically the same planes, okay, were used in order to actually take photos, bomb, and do the assessment of the target destruction. They were automatically being dispatched as soon as the targets were not being destroyed, okay? And all the information and the intelligence that they were gathering while still being in the air without landing was actually communicated back to do the assessment and get the new orders. So this cycle to basically do militarily the same thing, which is destroy a target, was in the order of magnitude of minutes. Okay? So on one side, in the Second World War, we have this operational cycle that takes 3 days that has been reduced into an operational cycle that takes a few minutes at a time. Now, what has made this possible? Okay? And this was made possible because of course, the communication and the information technology we have today. Okay? And that is the advantage that high-tech armies have today. Now, at the same time as information technology allows the army to have much smaller cycles, it exposes them to greater dangers. And these are the dangers that basically people can listen into their communications, decrypt them, but most importantly, find their locations and do traffic analysis and try to avoid being destroyed. And really, trying to avoid being subject to traffic analysis is creating such an expense on the military system that is widening this circle. So from minutes, you're again forced to use less communications and go back to the realm of a few hours or a few days in order to perform your operations. And for a modern army, this is extremely dangerous. So let's look at some concrete attacks from the military world. Before even the existence of radio communications, people were already realizing that one could extract information that is not just textual. So they were planting wires next to, in the earth basically, and tapping the earth returns of the adversaries during the trench warfare. And every time there was a certain pattern of transmission, they were expecting basically the artillery to start shelling them. But of course, the heyday of traffic analysis techniques was when radio communication started becoming dominant, and in particular at sea. At sea, it's quite difficult to actually have cables, and even optical communication is difficult under bad weather conditions, so ships have to talk by radio, and other ships will be intercepting their radio communications and basically trying to get their intentions. In particular, operators that were sending Morse messages, even encrypted Morse messages, had a very particular what was called a hand. Different operators type Morse with a slightly different way, in the same way that my voice is different from your voice. And other operators were becoming very, very good at picking up this signature and telling which ship is where by the fact that their operators were the same. And ships were identified just by the operator's hand. Many more examples that I'm not going to go through. In particular, identification of radio equipment is also relevant to GSM phones today. But the question is, why is traffic analysis, rather than looking at content, so valuable? And in the military world, it's really valuable because it offers a lot of information. And it is actually cheaper to extract and automatically process than message content. Okay? For message content, you have to have someone translating it and understanding it, and then condensing it into an intelligence report, whereas to some extent traffic analysis is just automatically picking up a lot of signals, doing classification of them, and then passing them on to analysts. Now, each signal is of less value, but the aggregate actually gives you a lot of information. And of course, one cannot see traffic analysis versus cryptanalysis because they're complementary. Modern intelligence uses traffic analysis to select which targets to actually listen in more carefully to. Of course, and this is going to be maybe a recurrent theme in this presentation, there is also the issue of jamming communications and which communications jam, which is also associated with traffic analysis techniques. Now, without wanting to bore you with the military world, it's interesting to see how these guys tried to solve the traffic analysis problem and provide defenses in order to maybe get inspired about what we can do. And in the military world, there has been quite a few technologies to try to prevent basically leaking information by telling the adversary that there is a communication or telling the adversary who's talking with whom. And the kind of recurrent principle underlying these techniques is the fact that you try to make the adversary spend a lot of resources, which is time and energy. Energy in the terms of physical energy, not human capital, in order to detect and possibly jam the communications. So one key technique is frequency hopping. What you do when you transmit is you just use a pseudo-random number generator that is cryptographically strong and change your frequencies all the time. Someone who does not have the hopping sequence basically will have to listen into the whole spectrum, meaning that they will have to use a lot more power than you have to use in order to transmit. Okay? So there is an imbalance. Maybe you can win this way. A second technique is to use spread spectrum, which is slightly too complex to explain in huge detail here. But basically, instead of sending a high-power signal on single frequencies, even frequencies that hop, you just spread your signal over a very, very large chunk of the bandwidth, and using a secret spreading sequence that allows you to recover it. Someone who doesn't know that sequence will find it very hard to actually detect that signal under the noise floor, and will have to use extremely precise equipment to cancel the thermal noise in the circuitry and pick up your signal. And then there are other more esoteric technologies like burst communications. You most of the time not talk, and then suddenly send a really high frequency signal with a lot of data, and then stop talking again while you move probably. But the most important thing, and this is, I think, a recurrent theme in military security, is that all of this technology was really supported by clear security policies. For example, ships about to engage in some operation at sea were not to talk until basically they strike the enemy. And doctrine, of course, and training, and people knowing when to transmit and when not to transmit and what information is leaked. And maybe this is one of the key differences with the civilian kind of networks, that basically our users are not really trained, or they don't even want to be aware that security exists, or let alone do anything about it. Now, some of these technologies that were first created for military purposes, we can see them around. So, for example, GSM phones use some kinds of frequency hoppings to avoid actually bands that are used by microwaves and such things, not actually to avoid being intercepted. ADSL modems use at their base some form of direct sequence spread spectrum. Actually, it's with orthogonal codes, which is, again, just to avoid interference rather than have covert communications. And some products also use meteor scattering, which is this burst communication technique, to provide cheap communications in the desert and such things. A key reference for all that is actually Ross Anderson's book, Security Engineering. He has a whole chapter on military techniques. But of course, we're not really that interested on military techniques, because we leave that to the people who are in the army. We're interested about the internet. And the internet is not quite as hostile as the military networks. Of course, it's used for commercial purposes, people use it, governments use it, it's sometimes part of the critical infrastructure, and even the military use it, so sometimes it is actually quite sensitive. But overall, if there are attacks on the internet, usually no one gets killed. Of course, it's a confederation of networks, there are different jurisdictions, but I guess that doesn't need, in this audience, to be explained. Lots of different transport technologies, so we can't really think that there is just one technology. And there are basically, what defines the internet is a set of common routing protocols, the IP protocols. And what is interesting about them when it comes to traffic analysis is that there is no protection of the routing information. Okay? So if you have an IP packet, you know where it came from, you know where it goes. If you send an email, the to and from address are there, and that basically goes on for all the established protocols. Okay? So to a first approximation, most of the traffic analysis techniques should work fine. And these networks, the internet network protocol networks, are not actually protected at all. And on top of that, because some people believed a few years ago that, well, you can't really eavesdrop communications anyway because they are in a router somewhere in the backbone, new technologies make that really possible, because of course everybody's using wireless now. The encryption of wireless is so-so, particularly when I wrote this slide, it was pretty much broken. Everybody is using peer-to-peer and overlay networks, which means that your communications are getting relayed over other people that can see all your traffic data, who's talking with whom, who you're talking with in clear. And so there are just many more opportunities to collect data. And at some point, we will have to start thinking, what kind of information is this traffic data leaking about us that is so easily accessible to everybody else? And of course, it's not just the case that you need clever mathematicians to look at this information, let's say, to extract intelligence about you, because once someone writes a script or a good application that does traffic analysis, then everybody can run it and everybody can just see the results. You don't have to all start from scratch coding and not making it, basically. Okay? So there is one particular interesting let's say, technological trend, which is that telephony nowadays is going to more and more be based on IP. And for many years, law enforcement has been very interested in knowing who's talking with whom. This is how they hunt organized crime and terrorists and all that stuff. So now it's going to become an issue on performing this kind of intelligence gathering on the internet as well. Okay? But before going too much into this kind of high-level gaining intelligence, let's see how one could use in practice traffic information in order to break quite established security protocols. Oops, I'm going back instead of forward. Okay. So everybody, I guess, here is using the secure shell protocols, and everything is encrypted. The cryptographic handshake ensures that you're talking to who you think you're talking, so everything should be fine in theory. It's the best of the best protocols. But of course, traffic analysis can still leak some information. Now, imagine you connect at home and then you further type a password to access your mailbox or to log in into other systems. Now, what is happening? Every time you press a key, basically a packet is generated that is perfectly well encrypted and sent back to your server. Okay? And of course, it's quite trivial to think that depending on the position of the keys on your keyboard, it takes you a slightly different time to press consecutive keys, okay? So O and P maybe are very close to each other, so it's a short time. Q and W are the same, but Q and P are not quite that close, and therefore the intertiming will tell you something. And this leads to an attack that was described by Song and al. And they observed basically the intertime delay between consecutive keystrokes and managed to basically not completely break the password you were transmitting, but reduce enough the uncertainty of this password to be much easier to brute force and crack. Okay? So here we see a really traditional security protocol, OpenSSH or a secure shell in any invocation of it, a really classic security property, namely being able to protect the privacy of your passwords, and an attack based on traffic analysis, i.e. looking at the patterns basically on the network of the packets that symbolize the keystrokes, managed to violate this property. Now, Rubin and al. Further noticed that different people have actually a different pattern of typing. Okay? So fundamentally how you type is very much like your face or like your voice. It really characterizes you. So they say that, they say because I actually never seen it running, they say that they can create good models of your typing behavior. And again, by observing you, for example, composing an email over Pine, if you connect through SSH to a terminal and use Pine, they can actually tell who you are. So even if you think you're anonymous, just because you logged into a system that everybody in your university is using, and basically because you use SSH, no one can really see who you are and all these things. It's not quite the case, because the timing of your keystrokes will actually betray who you are. So this is about SSH, and let's look a bit at web security and SSL. Now, many websites, as you know, will use SSL in order to hide your patterns of behavior. So let's say you're accessing some medical information website. Some of the pages you're accessing might be perfectly innocuous. They're going to be talking about how to treat symptoms of the flu. Other pages might actually be slightly more compromising. They might be talking about sexually transmitted diseases, and the fact that you start browsing those pages, if it was made public, clearly indicates that you have an interest in this field and maybe leaks information about your state of health. So many websites, of course, choose to encrypt all the traffic to make sure that no one can tell which pages you are browsing, the simple flu ones or the sexually transmitted diseases ones. Now, there is a whole line of research, I just mentioned 2 papers here of Hinz and al. And Simon and al. That basically says, well, SSL really is hiding the content of the communications, but it's actually not disturbing much the timing of the requests and the replies from the website, and it is not also disrupting very much the length of the packets that are being sent from this website. So if you are going to receive an image, for example, from this website, it's padded a bit down to the block size, basically, of the cipher used, but no more than that. And this line of research, basically, what they do is they browse a lot of websites, they create profiles out of these websites, and then they look at encrypted SSL connections, and just from the intertime of the packets and the resources that you use, they can infer, according again to their research, which websites you are browsing and which particular resources on a particular website you are browsing, despite the fact that it is in an SSL connection. So here we have SSL, and it's not really helping your privacy very much, as one would think when they see the little key chain thing on the browser. Okay? Now, I have myself done a bit of research on this field, and what I have found is that very often, and this was actually the subject of my talk the first time I talked at the CCC, very often looking at a single request doesn't give you much information. Pictures have roughly all the same size and all these things. So one can actually have more sophisticated statistical models of how web pages look. And by looking at a consecutive set of requests, because users will mostly be using links to go from one page to the other, you are actually able as an attacker to track much better which pages a user is accessing. Okay? So using SSL to hide your web clickstream is just not effective against traffic analysis attacks such as these. Now, Some people have actually argued that this is not, technically speaking, a traffic analysis attack, but I'll present it anyway because it's just cool. Now, sometimes a website may have an interest in finding out which other websites you have visited. Okay? And of course, you're not going to tell them because you like your privacy. So there has been a whole sequence of attacks devised that could actually infer that. What they do is they embed within the page of the site they control, okay, that you've just gone to, a set of resources from the other website. And they rely on the fact that modern browsers perform quite a bit of caching, particularly when it comes to images. And then basically the time it takes you to load the resources from the website that they would like to find out if you have already accessed. If the time it takes you is quite long, it means that actually your browser is going to this other site, fetching the images and displaying them to you. Well, in fact, they're not displayed. They're just a 1 pixel by 1 pixel on the browser, which you cannot see. But if the time it takes your browser to load these images is actually quite short, it means that they were locally cached, which leaks information about the fact that you have already browsed this website. Okay? So if you're Microsoft, let's say, you would like to find out if the user that is right now browsing the Microsoft.com website has already browsed the Apple website, then you just embed some resources and check the timings, and you can basically get quite accurate readings about the fact that they have been looking at your competitor's site. Okay? And the interesting thing is that anonymizing proxies don't really help in this case because they don't really change the caching properties of your browsers. And if you do change the caching properties of your browsers, it's going to be pretty slow. So the attack is quite robust, and it was actually proposed by Felton and all. Now, it's not quite a traffic analysis attack in that you don't really look at the traffic on the wire per se, but it still uses the same kind of techniques of remote observation that are used in lots of traffic analysis attacks. This is why it's relevant. Now, let's move into the realm of identification here. It's quite an interesting thing, both for people doing law enforcement or for people who try to attack networks to understand how networks look like, inside NATs, outside NATs, behind firewalls, and all these things. So the first question that might be interesting to ask about a network is, how can you find out if two different network addresses, two different IP addresses that maybe you're talking to or maybe are accessing some of your nodes in a distributed system are actually the same machine? Maybe it's some hacker that tries to masquerade as two different machines or two different people to perform an attack. Okay? And this is actually something that Stephen Murdoch has talked at great length previously here, so probably I don't have to go into huge details in this audience about it. But people at CAIDA, who are a network monitoring kind of research group, have observed that computers have particular quartz crystals that have a very specific drift. Okay? And each computer has a crystal with its own drift. And what they do then is they send ICMP echo packets and also TCP packets with a timestamp request to find out what the remote time is. And then they just try to detect how the two different machines that you try to establish if it is the same one or not have their clocks drifting. And after some time, they're able to basically say, no, these clocks are drifting independently, at which point they conclude that the machines must be different, or they're drifting at the same pace, okay? And then they make a statistical judgment as to whether it is actually significant enough to be the same machine or not. Now, this attack was explored to kind of ridiculous length by Stephen Murdoch, who's able to basically pinpoint now if hidden services in Tor are the same machine as some other machine you're accessing in the internet. And I refer you to his paper and talk to find out if your machine is hot or not. Now, there is the inverse problem that sometimes you'd like to know. You have a single IP address, let's say, that is accessing your site or you're interacting with. And of course, this single machine could actually be a gateway or a NAT and hide behind it multiple machines. So you'd like to know how many machines are there behind this IP address. Okay? Now, Steven Bellovin, who's security expert, quite renowned, has pointed out that quite a few TCP/IP stack have a very particular property, which is that their IP ID field, which is a field in the IP header that allows you to actually fragment and defragment IP packets reliably, their IP ID field is chosen, let's say, with a very particular, in a very particular way, which is just a counter. Okay? So when a machine will talk to another machine, and this is only per pair of machines, the IP ID field will just be a counter that gets basically incremented every time a packet is sent out. Okay? This is quite a rational design choice because IP IDs have to be unique, and the best way to ensure that is to actually choose consecutive IDs until they wrap around. But of course, if you have different machines behind a NAT, and they all have a conversation with you, they will all have independent counters as their IP ID field. Okay? And by observing how many such independent counters there are, he basically is able to make a judgment as to how many machines there are actually behind these networks. It's a very nice paper, and it has pretty graphs showing how you can fit lines through these IP counters that you receive in order to actually make an estimate about how big a network is behind a NAT, for example. Okay? Again, this is quite sophisticated as an attack. I think Nmap is also using IP ID tricks to do lots of things like that. And also indirect port scannings and these things. So traffic analysis attacks like this are also nowadays getting more and more into tools that people can use. Now, this was all about looking at, on one side, traditional security protocols like OpenSSH and OpenSSL, or any variants of SSH and SSL. Then we really talked about doing a bit of network monitoring using traffic data. So far, so good. Another community with a long-standing interest in looking at traffic data and getting intelligence are the people who do intrusion detection. In particular, these days it's quite popular as a sport to control botnets, and these guys would like to have a way of detecting the botnets that are running, let's say, within a corporate network. And in particular, they care about detecting what they call stepping stones, which are machines that are used just as a relay to attack other machines in the network. Okay? And they have a very simplistic model of these machines, let's say. It's a compromised machine within your network, okay? That when basically it receives streams of traffic, it just redirects them somewhere else. So basically it's kind of a primitive anonymizer, shall we say. And there is a lot of literature on trying to detect these stepping stone machines, and the kind of common idea is that you have an intrusion detection system which sits on your gateway to your private network, and then it looks at streams of traffic coming in and streams of traffic coming out, and kind of correlates the patterns within them. And if it sees that consistently a stream of traffic coming out is the same as a stream of traffic coming in, just by its shape, not its content, okay, it says, maybe we have a relay in our network, maybe it's a compromised machine. Now, sometimes, of course, it's going to be legitimate activity, such as a secure shell connection being bounced back and forth and such things, but sometimes they actually catch intrusions this way. Now, this is the passive version when you just look and try to detect, but of course there is a slightly more active version where the gateway or the intrusion detection system disrupts slightly the timing of the streams coming in and tries to basically detect this watermark, okay, in the streams of traffic coming out. So this is an active attack which makes it much faster and much cheaper. Okay, so coming from traffic analysis of anonymous communications, I find some of their assumptions quite naive in that we can do better anonymization than this simple relaying. But it's interesting that their approach apparently still works in the naive cases. Now, we have talked a lot about traffic information, i.e. Alice talks to Bob at 8 o'clock for 10 minutes, or for 100 kilobytes if it is an email. But of course, as I said, these days we all go around with mobile phones and laptops that connect to Wi-Fi, and these days we also have a little Sputnik on us. And all that is giving out location information. It basically can tell base stations where we are. Now, This is a relatively new field, i.e. the field of trying to extract from this location information high-level intelligence. Okay? In particular, Pasquale and al. Logged a lot of traffic at Hackers at Large, which was a hacker conference, and also at his home university in KTH. And he looked at the traffic and basically created models that could infer where people are going, which talks, which lectures they attended, and basically also relationships between people. And it is actually rather counterintuitive that your location is not just giving information about, of course, your location and the fact that you're in this lecture, but also about your relations to other people, okay? And the reason for that is because if I see you all the time being in the same cells or in the same room or sitting next to someone in particular, okay, and I see that happening again and again and again, it is highly unlikely that you have absolutely no relation to that person, okay? So if I see you in the morning sitting next to someone and then in another random talk in the evening, probably the probability is that you know each other and that you have, chatted with each other and, you're sitting together. If I see you together with someone on a Saturday night at about 8 or 9 o'clock, it's quite likely that you're friends, because people don't hang around for work or with random people on a Saturday evening. If I see you on, let's say, Saturday at 5 o'clock in your home location, both of you, probably you're sleeping together, okay? So it is not just where you are, it is also who you know and what relationships you have with other people that is leaked via location information. Intel Cambridge ran a similar experiment. They basically took lots of Bluetooth devices and made them record who they see. And again, they discovered a couple that had devices that could see each other all night long, which was not common knowledge in the lab. And MIT ran a similar project where they gave students 100 phones. And what is interesting about the reality mining project is that all the data is available online. You can send them an email and mine happily and see what you can find. Okay, now I talked about low-level information, breaking passwords, finding out about network topologies, and to some extent, okay, the relationship between people is higher level, but the stepping stone is still intrusion detection lower level. But I guess I don't have to convince you that the information about your communication is also leaking a lot of information about your higher self. What are your intentions? What are your beliefs? What is your job? What are your sexual preferences, your political views, and all these things? In particular, the field of sociology and peer-to-peer networking is kind of merging, okay? This idea that we had in 99 or 98 that, people talk at random and we just have to talk at random and all that stuff is not quite true, and we know it now. Human networks have a very specific topology. It has a particular degree distribution that turns out to be a power law. If I have two friends, they are more likely to know each other than two random people. And in particular, human networks are navigable, meaning that it is actually quite easy to find someone else by relaying communication than a random topology. So we know that human networks have a very specific topology, and of course, traffic analysis can be used to infer that topology, okay? And lots of people have caught on to that. In particular, there is a Dutch criminologist that has worked really closely to the Dutch police who said, using traffic analysis, I can tell you who to arrest in order to maximally disrupt drugs network, for example. Other people, like Nagaraj and Anderson in Cambridge University, looked at it from the point of view of disrupting, again, networks, and have found particular peer-to-peer architectures that try to protect against it. But what is really interesting is that it seems that this field is so mature in the closed communities of intelligence and law enforcement that it has 20 whole pages devoted to it in the newly published counterinsurgency doctrine manual of the US Army. Okay, this is not really where you expect to find sociology, yet Appendix B, which is 20 pages, is devoted on basically how to find out who's friends with whom and basically who to kill in order to better win your war. Now, I don't want to be overly negative about all this because, of course, traffic analysis techniques can also be used for good. Google PageRank is a good example, basically, of trying to infer where people would be navigating in order to give you pages of most interest. Advocato is a social network, and there are many more examples like this. Now, I don't want to focus too much on traffic analysis resistance because this is the good old field of anonymous communications. that Roger Dingeldine has given a clear overview yesterday. So basically, there has been research going on into anonymous communications that try to hide the routing information since '81. Very much it was theoretical till the mid-90s, let's say, when the first kind of cryptographically strong remailers like Mixmaster were developed. And of course, when it comes to web anonymity, we have JAP, the Java Anonymous Proxy from Dresden University, and Tor that Roger presented yesterday. Relatively, in the last 5 years, we had a lot of research in this field, and we have created a lot of knowledge on how to build this system, and a lot more actually on how to attack them. So if you are going to present or start coding your anonymous communication system and you think it's great, do talk to me and Roger and other people who have worked in this field before, and we'll tell you, well, our opinion, I guess, about its strength. So yeah, I'll not talk very much about all this. I'll just skip to conclusions. And before I actually reach the deep conclusions, I want to talk a bit about policy. Now, in Europe, and the US to some extent, we have this new piece of legislation about retaining all traffic data. Okay? And there is a clear connection to what I have been talking about all this time, which is that traffic data is really the kind of fuel that you're feeding into traffic analysis engines in order to get out results. Okay? And suddenly we have the European and national European and American legislator who says to all the communication providers, you have to keep all that data. Okay? You have to keep it for a certain amount of time, and you have to be able to give it to us for, the purpose of investigations and all these things. Okay? Now, what is the problem with that, of course? The problem is that this kind of policy introduces a systemic risk in the telecommunication networks we have. As I mentioned to you before, within the standard protocols that we're all using to communicate, there is actually no provision to protect against traffic analysis. All the traffic data is in clear, and now all the internet service providers and telco providers are actually mandated to keep it. Okay, so even if you said, oh, what is the probability that all this data is getting intercepted and used, suddenly now the probability is 100% by law. Okay? Now, of course, for the prevention of crime is a good idea, but covert communication is actually still possible, despite traffic analysis and despite basically all this traffic data retention. So what we have to do, I guess, in the next few years is to try to explain to the public at large and legislators the extent to which this data that is being retained can be used for attack. It can be used for attack at low levels. It can be used for attack at high levels. It can violate your privacy as much as your network security properties. Okay? And this has really been understated, and I think that if we had a much concerted effort in exposing that fact to the public and the legislators, we would have very different policies in place. Of course, the second issue is the whole peer-to-peer information warfare we've been observing. People try to pirate music, and that's great. And people try to prevent them from doing that, and that's their business too. So it's basically information warfare for real out there. Okay? And traffic analysis is really at the heart of it. Okay? Because on one side, the people who try to share try to not give a signature, not to be blocked, not to be detected, not to be identifiable. On the other side, of course, the people, and there are companies doing this business, who try to file suits against them, will try to detect when they're doing it, will try to filter them out if they're ISPs, and will try to identify them to sue them. Okay? So we have a huge arms race going on out there, and techniques are getting more and more sophisticated on both sides. And of course, it's a policy issue. Do we want this information warfare to be happening out there? Is that really what our information networks are for? And is basically protecting the music industry, which with its business models from, I don't know, 100 years ago, really worth, having this hostile environment in peer-to-peer networks? I mean, that's a policy decision that we have to make. And of course, privacy, I guess, and data protection are the ultimate question, okay? It is really not clear to people that who they talk to is sensitive information, and the techniques for mining this produce such high quality results okay, that no one really could just guess it, okay? Yet our definitions of data protection and what is sensitive data and all these things really don't take into account all these techniques. They say, oh, if in a form you're asked if you're a vegetarian or not, and you reply one way or the other, this is personal information. But you know what? What you have shopped in the supermarket is not really that sensitive, even though, you know, if it never really contains meat, it's pretty much clear that you're a vegetarian. So you can extract the same high-level information, yet they kind of come under completely different regimes. On one side you have high, you know, sensitive, let's say, information, and on the other side you just have aggregate data which no one really thinks that is sensitive. Now, privacy protection, of course, is quite back when it comes to these issues, while privacy violators are systematically doing mining in order to do better marketing and sell you their stuff. And of course, they are well funded to do this, okay? Now, just to conclude, because I only have 5 minutes, which I want to devote to questions, I think that traffic analysis as a discipline has really been neglected. I was having dinner with quite an expert in computer security, and we were having this discussion of, oh, you know, if all the traffic is encrypted in the networks, then, you know, even if you own a router, you can't really do much. Well, I hope my talk so far has convinced you that just encrypting the data is part of the solution, but is definitely not the whole solution to secure a system. Who's talking with whom, when, how, where they are, is already leaking a lot of information at all levels. Now, I spent quite some time talking about the military world. This is a closed community that I don't know much about. If you have more information about it, I'd be delighted to hear it. But I hope that we can apply some of the paradigms for covert communications to civilian networks as well, of course. And just a warning to say that the level of sophistication of the attacks we've seen is still not state-of-the-art. I'm sure that in the next few years we will do much better in terms of traffic analysis attacks, but it is already sophisticated enough for people just coming up with a clever idea to have quite a high probability of this idea already having been considered and broken before. So please, I urge you to work on this field. It's a fascinating field, but I also urge you to talk to people who are already in there and read what has been done so far, because it's quite worthwhile and non-obvious, okay? Securing communications against traffic analysis is still expensive and very fragile. Tor is a deployed network, and it's a great product to use, but it is definitely no silver bullet, and we're working on doing better, but it's not an easy task. And of course, because it is not an easy task to technologically protect our networks, it is extremely important to at least have policies that protect our networks, okay? To not be logging traffic data, to make it harder to get at the traffic data. Sadly, today we're in a policy environment that does exactly the opposite. It mandates people to retain the traffic data and makes it easy for all sorts of people to access it. And this fact, along with the fact that there is a full-scale information warfare in peer-to-peer networks, make covert networking and all that stuff, you know, even more important to deploy. Thank you. We have maybe a few minutes for questions.
Hi. I want to come back to the topic of secure shell and identifying users by their way of typing and the time shift that they present by typing. So I don't know if this has been addressed before, but maybe it's just possible by shifting the packets automatically by the secure shell application with some kind of SHA-512 checksum and some microseconds, which you get out of the checksum. So my question is, what are the time differences that I measure to identify a person? What are the numbers I need?
Right. So I think you're completely right. There are countermeasures that one could deploy. So the timing differences are extremely subtle. I don't have the numbers exactly, but they're just milliseconds basically as you type. And of course you need a lot of aggregate data and quite a lengthy email to perform accurate identification according to Rubin. Okay? I think what is really important is, despite the fact that the countermeasures are, as you say, quite simple to implement, just add enough jitter at random and all these things, it was not even a security requirement when Secure Shell was being designed. Okay? So it's not the case that the countermeasure in this particular case is really hard to implement. It was just never considered an issue. And OpenSSL and SSL as a protocol and TLS, its successor, is exactly the same, in that you can see in the standard that it actually warns you that it doesn't protect against traffic analysis. It's in the introduction and the preamble. Yet there is actually no attempt to shift it towards protecting a bit more.
Hey, George. I have a different kind of question for you. Whoa. Hey. Okay. Hey, George. You spoke a lot of traffic analysis and a lot of different issues in the field. I would like to actually ask you how you believe this research can be directed to actual content inspection. And what I mean by that is not necessarily IDS or dissecting protocols, but rather, for example, there is a lot of data in the world and a lot of trouble collecting it. But once it's collected, the actual trouble is getting the information you need. So it's not always about getting more data to establish a baseline for how people type, but rather what's actually interesting in all that. So have you done any work, or do you know of others who have done work in that particular field? Oh, hey. Thanks.
So, okay. What I do not want you to think when you come out of here is to say, oh, this George dude, you know, he talked in general terms about, you know, trends and ideas that may actually work out or not. So this is a network diagram. It was basically mined from the mailing list of a large political network in the media. And when they saw actually this diagram, they pretty much freaked out. Not that they have much to hide, but you know, being political types, they're a bit aware of privacy in communications. So indeed, and maybe your question is kind of related to this, you know, this is pretty, but it doesn't tell you much. Okay, this is basically network diagrams with some heuristics on which links matter, which links don't matter between mailing lists and people. So the names are quite small in order to avoid the privacy violation, and you won't find these slides online. What we do then is basically we apply a whole sequence of heuristics and all that stuff to that data in order to extract high-level intelligence. So basically this is pretty much the same diagram. It's actually not homomorphic, but as you can see, it's much more simplified. And we actually took this real data and tried to just keep what is important, i.e. finding out the people who turn out to be bridges between two different spaces in this network. Okay, and we came up with a list of 100 people in order that you should shoot in order to actually completely fragment this network. So yes, traffic analysis has a lot in common with the field of information retrieval and data mining. It is just that it is specialized on looking at traffic patterns instead of the actual contents of documents. And yes, there has been a fair amount of work in doing traffic analysis on that stuff and target selection. Other questions? Yes. Yes.
Less of a question, more of a follow-up to the question about SSH. There's probably some SSH experts in the crowd, so please stop me if I'm wrong, but I believe when SSH is entering a password, as in keyboard, as in the password authentication scheme, the password is sent as a burst. Mm-hmm. But when you're typing in a password, for example, tunneling one SSH session within another, the keyboard strokes have gone through. So you can't add noise because SSH doesn't know where the password is.
That's right.
And if you do add noise to everything, then SSH becomes annoying.
It depends how much noise I think would make the product unusable. It's not clear that the signal that you have from individual keystrokes is actually that much. So maybe introducing a tiny little bit of noise would help enough and not make the thing unusable. You have to go back to, I guess, the timing analysis that Ruben did to find out if it would be annoying all the time or not. But yes, you'd have to do it all the time.
Back to this very interesting example about the intermedia network. Is it then different if the whole network, everybody or the hosts in the network, they use Tor then? Is that then a solution, or does that bring out other exposable?
So that was actually exactly the purpose of our research when we did this analysis. We tried to look at to what extent the network would be susceptible to target selection, i.e. someone observing who's using the mailing list, who's actually really important in that network and who's not, and going and taking them away or telling them not to participate anymore. And we wanted to exactly answer the question you asked, whether using an anonymous communication system would protect them. And the question is, well, the answer is a bit, but not very much. So the attacker would have a very much harder time to find who basically to disrupt, but after a while they would anyway find who to disrupt just by the amount of communications they would be doing. Now, using Tor for this purpose is not quite right, because we're talking more about email-like communication, so it would be more like remailers. But I urge you actually to read a paper that I've written called The Economics of Mass Surveillance, which discusses exactly that whole thing, and all the nuances are in there. It's not a very simple question to answer, but basically the answer is a bit negative. It's not clear that just using anonymizing technologies would help all that much. We hope we can make them better so that they do help. Sorry. Okay, so I see no more. Oh, I see more hands, maybe, or not. I don't know. No? Oh, yes.
Hello, thanks for your interesting talk. A question to the measurement of time delay between computers to identify them as the same machines. Does NTP have any effect on your measurements?
Right. So I'm not sure if you actually refer to the attack that relies on the quartz crystals, or the attacks that rely on the IP-ID signatures.
To the quartz crystals.
Right. I guess Stephen is the resident specialist here, so I should stand corrected. Maybe you want to actually talk that question, because otherwise I'll embarrass myself. Stephen has spent a long time with a hairdryer pointed at a computer and a stopwatch, basically. And he's going to get a PhD out of it very soon.
It was actually a desk lamp. It was a desk lamp I had pointed at the computer. The question of NTP is slightly complicated. Firstly, the timestamps that... Closer. The timestamps that I was looking at were from the TCP timestamp field, and that commonly happens on OpenBSD, Windows, and Linux before NTP correction. But even if NTP correction were applied, as it is for the ICMP clock or the TCP initial sequence number clock, then it should be possible to remove that, because NTP is not designed to filter out effects that are as fast as I was measuring. So even though it's over a few hours, NTP is designed to smooth things over several days, because if it reacted very fast, it would have problems because of network latency for the NTP connections, and the clock would become unstable. And unstable clocks are generally worse than slightly inaccurate clocks.
Okay. I'm being told that our time is up, so just one final announcement. We have a quite large now research group at KU Leuven, which is next to Brussels, looking at traffic analysis issues. We're looking for bright people who would like to join us to do traffic analysis research. If you think you're interested in doing that, please talk to me or send me an email. Also, the first and best place to talk about anonymous communications and traffic analysis is the Privacy Enhancing Technologies workshop. It's going to be in June, I think, in Ottawa, Canada this year, so please come. The anonymity bibliography is really important. If you want to do anything on traffic analysis or anonymity, go and check it out. And of course, I, as well as Roger and Stephen, will always be available here to chat to you if you have any ideas. Thank you.